Okay, now this is where the previous equation of decomposing the acceleration vector comes into play. Now we had previously A, which is the acceleration vector, is equal to dv dt, the unit tangent vector, plus v squared over rho, the unit normal vector here. Okay, and we know that the acceleration vector is here. However, let's just say for a minute we want to write this one in terms, we want to write the acceleration in terms of these two components over here. You cannot see the relationship over here because we have yet to find the unit tangent vector and the unit normal vector. But first, let us just go a step at a time. Let's just find the tangential component, which is dv dt. Okay, and what do we know? dv dt, we have it over here. This is the speed, which is root 5 over t. So we differentiate that, we get root 5. Sorry, we get, yes, root 5. So we got this component over here, but then now, how are we going to find this component over here? The normal component. Well, we need the rho here, and if for us to find rho, we need kappa. And for us to find kappa, we need to differentiate the unit tangent vector in terms of s. Okay, right now it's going to be a problem because it seems to me that it's going to be very difficult to express the position vector in terms of s via the equation which we have shown time and time again is the integrate of the magnitude of the first derivative of the position vector. Okay? However, there is another way, because if we were to envision the curve like this, okay, and just like how I've shown you previously, if the acceleration is going in this way, there are two components, which is the tangent and the normal. Okay? And then, if this is unit and if this is unit, that means it would seem to me that the length, this length here times this length here squared, add up with this length here squared, would give us the magnitude squared via the Pythagoras theorem, which all of you should be familiar with. There's a right angle triangle over here. Okay, that means this magnitude here, and is related, these three lengths are related by Pythagoras theorem. This square plus this square equals to this square. And this, what we know, is AT, and this is AN. And we need to find AN over here. We have AT, which we just found out here, and we got the magnitude of the acceleration, which is equal to here. And that is how we find AN using some geometric properties, which is quite interesting, I must add. So let's just see what we get. AT squared plus AN squared, bearing in mind AN is the normal component, which is equal to this, is equal to the magnitude of the acceleration squared, just like I've shown you over here. So this is equal to 5 plus t squared. We're just simply squaring that. We write the normal component here, and then we take the tangential component and we square it, so it's equal to 5. So then we minus off the 2, AN is equal to t squared, and AN is equal to t because t is more than 0. And there we go. So now we got this one over here. AN is equal to t. But we know that the normal component is also equal to this, which is v squared over rho equals to t. Okay? Well, let's just look about it in a minute, because v squared is the speed function. We have that over here. We square that, and rho is 1 over kappa. Rho is 1 over kappa, so 1 over rho is equal to kappa. So if we were to rewrite this, is kappa times by velocity squared, which we will do it immediately as 5t squared, and is equal to t. Because we found out that the normal component via Pythagoras theorem, the geometric aspect is equal to t. So from this, we can find kappa, which is equal to 1 over 5t. Now, isn't that quite interesting? Substituting this back inside here, we got root 5, and this one over here is equal to t, and we got kappa equal to 1 over 5t. These are all the results that we have. Okay, now I would like to take a minute to really look at this because I think it's fairly interesting. 1 over 5t. That's the value of kappa that we have. Okay, what does this actually mean? Well, we have shown previously that in order to get this value, we need the value of kappa over here. First, we can try to go from here, differentiating with respect to s, okay? And then write in terms of s, differentiating this with respect to s, and then get the value of kappa, because kappa is equal to the unit tangent vector differentiate by s. So whatever the case may be, we need to write this in terms of s. We get kappa and then we can now find the unit normal vector. However, the other way is to just go from here, written in t, differentiate that and differentiate that to get the acceleration, find the magnitude of the acceleration over here, and using a geometric property of Pythagoras theorem, get an over here. And likewise, using that method, we again get an. Now, this is two ways to approach the problem of finding the normal component. And which method you use really depends on what you start out with. Because if you start out with a position vector in terms of t, I should believe that this is a much easier way than using the geometric property. Okay, but if you start out one in terms of s, then you could immediately go over here, find kappa, and then substitute inside, find kappa, find rho, and substitute inside over here to get an. So really, this is one of the reasons why I've been emphasizing a lot that we just keep the parameter as it is, because we really don't know on how we should tackle the problem until we look at the whole, until we look at the problem in its entirety. Because at times, sometimes we may want to differentiate by s to get kappa and go over here, but in other times, when we get something as complicated as this, it's difficult enough to substitute s inside there. And that is why we will do it this way. Okay, but enough for that now, because we want to finish up by looking at this one over here, this interesting aspect over here. Kappa equals to 1 over 5t. Remember, kappa is described as curvature, which is also as the amount of bending. So what is the geometric relationship? Let's see, if t tends towards infinity, 1 divided by a big number, infinity, you will get 0. So the radius, the curvature is equal to 0, meaning to say that the tangential curve does not change given the change in the arc length. See, this is the change in the arc length, the tangential vector changes. However, if it's 0, the tangential vector does not change. That is to say, as t goes on and on to infinity, the curve would just shoot off to be a straight line, such as, like that. The curvature, kappa equals to 0. Conversely, if t tends towards 0 from, say, a right-hand side, that means as we go towards the starting point of the curve, 1 divided by 0 is a big number, which is infinity. That would say that kappa is infinitely steep. Now, it's quite difficult for me to draw that, but you can just imagine that the curve is really curving a lot to at that single point, such as maybe this. Okay, it's curving a lot into that single point. So this whole relationship between the curve can be seen from the value of kappa, which is the curvature of the curve, the amount of bending. Okay, let me see whether is that all that we have. Okay, now just to sum up, okay, the second part is really finding t and n. Sorry about that. Finding t and n, the unit tangent vector and the unit normal vector.